1894, Brooklyn, New York. The engineering reports from European-trained construction experts would never fully capture what they witnessed that winter morning. American concrete sidewalks, cracking apart after just 5 years. Through the steam and dust of Brooklyn's construction sites, European methods dominated every major building project with techniques that seemed proven by centuries of old-world experience. Traditional water-cement ratios of 60 to 70%, fast construction schedules, immediate profits. Yet they produced concrete that failed within decades while European engineers insisted their methods were superior. In European cities, concrete structures lasted generations using time-tested formulas. Each project followed established protocols, proven ratios, standard curing times, predictable outcomes. Most carried the confidence that comes from centuries of architectural tradition. The Americans were experimenting with construction philosophy the Europeans considered dangerously untested. Lower water-cement ratios, extended curing periods, scientific testing methods, quality standards that prioritize decades over immediate deadlines. 3,000 miles from European academies, the most decisive concrete revolution in construction history was beginning to reveal itself. Not in faster building, not in cheaper materials, but in the systematic durability that would outlast everything European tradition claimed was impossible. Frederick Ransom stood ankle-deep in muddy concrete outside the half-finished mechanics pavilion in San Francisco, watching European-trained foreman Heinrich Müller direct the pour with the confidence of a man who had never questioned a textbook. The mixture flowing from the wooden chutes carried the familiar consistency of European concrete, wet enough to flow easily into forms, mixed with a water-cement ratio of 65% that allowed crews to finish an entire floor in a single 10-hour shift. Muller's methods had built half of Chicago's downtown district, using techniques perfected in German engineering schools, where professors taught that construction speed determined project profitability and contractor survival. 65% water-cement ratio ensures workability, Muller announced to his crew, consulting the leather-bound notebook that contained formulas copied directly from Berlin Technical University. German methods have built cities across Europe for 200 years. Why would we experiment when proven science already exists? The workers nodded respectfully, trusting expertise that came with old-world authority and the backing of established engineering firms that dominated American construction contracts. Ransom bent down and scooped a handful of the freshly poured concrete, feeling its texture between his fingers while mentally calculating the implications of that extra water content. Every additional percentage point of water above the optimal ratio created microscopic gaps that would weaken the final structure, but European engineers prioritized immediate workability over long-term durability because their construction contracts rarely included maintenance responsibilities beyond the first 5 years. American contractors had adopted these methods wholesale, assuming that techniques successful in European climates would perform equally well under American conditions that included more extreme temperature variations and different aggregate compositions. 3 blocks away, the concrete sidewalks installed just 18 months earlier already showed hairline cracks spreading in geometric patterns that revealed the internal stress created by excessive water content during the original pour. Ransom had documented similar failures across 6 American cities, carefully photographing crack patterns and collecting core samples that told a consistent story of premature deterioration. His mathematical analysis suggested that concrete mixed with 45% water-cement ratios could achieve 40% greater compressive strength, but the extended curing time required would triple construction schedules and eliminate the profit margins that kept contractors competitive in rapidly expanding American cities. The American market demands speed, declared Hermann Schussler during the monthly meeting of the San Francisco Engineering Society, his Prussian accent lending authority to arguments that dismissed untested innovations. European concrete formulas represent centuries of engineering refinement. Any deviation from proven methods introduces unnecessary risk to both structural integrity and project economics. Schussler's reputation as chief engineer for the Spring Valley Water Company gave weight to his technical opinions, and his encyclopedic knowledge of European engineering disasters made younger engineers reluctant to challenge his recommendations. Ransom listened to the familiar arguments while reviewing his private testing records that suggested a fundamentally different approach might revolutionize American construction. His experiments with California aggregate sources had revealed that American materials possess different chemical compositions than European limestone and sand, requiring modified mixing ratios to achieve optimal bonding between cement and aggregate particles. The slower-setting Portland cement manufactured in American plants also behaved differently during curing cycles, potentially allowing lower water-cement ratios without sacrificing workability if construction schedules accommodated extended hardening periods. European methods work because they have worked, Schussler continued, addressing the room with the measured confidence of a professor lecturing students. German engineers calculate every variable, test every component, verify every result through systematic protocols that eliminate guesswork from construction processes. American experimentation with untested concrete formulas will bankrupt any contractor foolish enough to abandon proven techniques for theoretical improvements. The financial reality supported Schussler's position with uncomfortable clarity. Construction companies operated on thin profit margins that required completing projects within predetermined schedules, and any method that extended construction timelines by weeks or months would make American contractors uncompetitive against European firms that could deliver buildings faster and cheaper using traditional techniques. The Panic of 1893 had already bankrupted dozens of construction companies, making contractors even more resistant to innovations that might increase costs or extend project timelines beyond what clients would accept. Ransom walked home through streets lined with buildings that represented the triumph of European engineering methods in American construction, but his trained eye noticed details that revealed troubling patterns. The concrete foundations of buildings completed just 10 years earlier showed surface deterioration that European concrete in similar climates rarely developed until after 30 years of service. American temperature cycles and humidity variations created stresses that European formulas had never been designed to accommodate, suggesting that wholesale adoption of old-world techniques might be creating infrastructure problems that would become critical within the next decade. That evening, Ransom sat at his drafting table calculating the mathematics of concrete chemistry while reviewing core samples collected from structures across Northern California. His analysis suggested that American concrete could achieve superior durability through scientific modification of traditional European ratios. But proving this theory would require a demonstration project large enough to convince skeptical contractors that extended construction schedules could be economically justified through reduced maintenance costs over decades rather than years. The challenge seemed almost impossible. American construction culture prioritized immediate results and quarterly profits, while his proposed methods required thinking in terms of generational durability that conflicted with every established business practice in the rapidly expanding construction industry. European engineers controlled most major contracts, and their proven methods carried the credibility of institutional success that no experimental American technique could match without extraordinary evidence of superior performance under real-world conditions. Richard Humphrey arrived at Ransom's workshop on a fog-shrouded morning in 1895, carrying a leather satchel filled with precision instruments that would transform concrete mixing from traditional craft into systematic science. The MIT-trained chemist had spent 2 years analyzing metal fatigue in railroad bridges. But Ransom's invitation to investigate concrete chemistry offered an opportunity to apply laboratory methods to construction materials that had never been subjected to rigorous scientific analysis. Humphrey's background in metallurgy provided unique insights into how materials behaved under stress over extended periods, knowledge that could revolutionize understanding of concrete durability if applied systematically to cement chemistry. European concrete fails because European engineers treat it like masonry instead of engineered material, Humphrey explained while unpacking his testing equipment in Ransom's makeshift laboratory. They measure by tradition rather than molecular behavior. Every batch mixed differently, every cure time estimated by weather observation, every strength calculation based on rules established before anyone understood cement hydration chemistry. His precision scales and compression testing apparatus represented the first systematic approach to concrete analysis west of the Mississippi River, equipment capable of measuring compressive strength to within 50 pounds per square inch, rather than the rough estimates that satisfied traditional construction practices. Ransom watched Humphrey prepare test cylinders with the methodical precision of a chemist analyzing unknown compounds, carefully controlling variables that European-trained engineers had never considered measurable. The first series of tests compared European standard concrete mixed at 65% water-cement ratio against Ransom's proposed 46% ratio. With identical aggregate sources and curing conditions to eliminate external variables that might compromise results. Humphrey's systematic approach required preparing dozens of identical test specimens, aging them under controlled conditions, then subjecting them to compression testing that would provide mathematical rather than observational evidence of superior performance. 46% water-cement ratio produces concrete testing at 4,500 pounds per square inch after 28 days, Humphrey announced while reviewing his laboratory notes 3 weeks later. European standard concrete from identical materials tests at 2,800 pounds per square inch under the same conditions. The difference represents 60% greater compressive strength through scientific control of mixing ratios rather than adherence to traditional formulas. The numbers provided mathematical proof that American concrete could surpass European performance, but only if contractors accepted extended curing schedules that conflicted with established business practices throughout the construction industry. The breakthrough came when Humphrey discovered that controlled aggregate sizing combined with systematic vibration during concrete pours could eliminate air pockets that weakened traditional European concrete. His metallurgy background had taught him that material density directly affected strength characteristics. And concrete, mixed with scientific precision, could achieve 15% higher density than European methods that relied on manual tamping and gravity settling to remove air bubbles. The vibration process required additional equipment and extended pour times, but the resulting concrete approached the density of natural stone while maintaining workability that satisfied construction crew requirements. Ransom's first major test came with the Pacific Coast Borax Company warehouse project in Oakland, where owner Francis Smith agreed to extended construction schedules in exchange for concrete that would require minimal maintenance over decades rather than years. The project allowed Ransom and Humphrey to implement their systematic approach under real construction conditions, mixing concrete to precise 46% water-cement ratios while using controlled aggregate sizing and mechanical vibration techniques that had never been attempted on a commercial scale. European-trained foremen initially resisted methods that seemed unnecessarily complicated, but Humphrey's patient explanations of the underlying chemistry gradually convinced skeptical workers that scientific precision could produce superior results. Every cubic yard mixed to identical specifications, Ransom insisted while supervising the warehouse foundation pour, personally checking water-cement ratios and aggregate proportions that traditional contractors estimated by visual observation. Every batch tested for consistency, every section vibrated systematically, every cure cycle monitored for temperature and humidity variations that affect final strength. The methodical approach required 3 weeks to complete foundation work that European methods could finish in 8 days. But Humphrey's ongoing testing confirmed that the concrete achieved design strength that exceeded European standards by substantial margins. The Alvord Lake Bridge Strengthening Project in 1897 provided additional validation when core samples from Ransom's original 1889 concrete showed zero deterioration after 8 years of service. Humphrey's analysis revealed that the low water cement ratio concrete had actually gained strength over time as residual cement continued hydrating, a phenomenon impossible with European high-water concrete that reached maximum strength within months of pouring, then gradually weakened through exposure to weather cycles. The discovery suggested that American scientific concrete could improve rather than deteriorate over decades, fundamentally challenging European assumptions about concrete aging that had influenced construction practices for centuries. Opposition intensified as word of Ransom's success spread through California construction circles, with established contractors arguing that scientific methods were impractical luxuries that American building budgets could not accommodate. Hermann Schussler publicly dismissed the warehouse project as an expensive experiment that proved nothing about large-scale construction viability, pointing out that extended curing schedules would make American contractors uncompetitive against European firms that could complete similar projects in half the time. The criticism carried weight with potential clients who measured construction success by completion speed rather than long-term durability, making it difficult for Ransom to secure additional projects that would demonstrate his methods on the scale necessary to convince skeptical engineers. Humphrey's systematic documentation gradually accumulated evidence that American scientific concrete represented a fundamental improvement over European traditional methods, but translating laboratory results into industry acceptance required overcoming decades of established practices and institutional resistance from engineering firms whose reputations depended on European techniques that had dominated American construction since the Industrial Revolution began transforming cities from coast to coast. John Eastwood stood in the rubble-strewn streets of San Francisco 3 days after the Great Earthquake, calculating reconstruction costs, while surrounded by the evidence of European concrete's catastrophic failure under seismic stress. Buildings constructed with traditional high-water cement ratios had crumbled into geometric patterns that revealed internal weaknesses invisible during normal conditions. But structures built with Ransom's methods remained intact despite ground acceleration that exceeded any European engineering specifications. The disaster created an unprecedented opportunity to demonstrate American concrete's superiority on a scale that would either validate scientific construction methods or destroy Ransom's reputation forever. 60,000 buildings destroyed, $200 million in damages, and every major contractor in California competing for reconstruction contracts, Eastwood observed while reviewing preliminary damage assessments that revealed telling patterns in structural survival rates. Buildings completed with Ransom's low-water cement concrete showed minimal damage despite experiencing identical seismic forces that had leveled adjacent structures built with European methods, providing dramatic evidence that scientific construction techniques could withstand natural disasters that traditional concrete could not survive. The earthquake had created a natural experiment that compared construction methods under extreme conditions impossible to replicate in laboratory testing. Ransom arrived from Oakland carrying detailed documentation of his concrete's performance during the earthquake, photographs and measurements that would support his bid for major reconstruction contracts against established European firms whose methods had been exposed as inadequate for American seismic conditions. The disaster had revealed that European concrete formulas developed for stable geological conditions failed catastrophically when subjected to ground movement that American Western cities experienced regularly, creating an opportunity to prove that American engineering solutions were not only superior but essential for construction in seismically active regions. The Ingalls Building Project in Cincinnati offered a different kind of proof when Melville Ingalls commissioned the world's first reinforced concrete skyscraper, using methods that combined Ransom's concrete chemistry with innovative structural design that European engineers considered impossible. The 16-story structure required concrete that could support vertical loads exceeding anything previously attempted, while maintaining the extended curing schedules that Ransom's methods demanded, testing both the engineering principles and economic viability of scientific concrete construction on an unprecedented scale. 16 stories of concrete mixed to 46% water-cement ratio. Every floor cured for minimum 28 days, every structural element tested for 5,200 pounds per square inch compressive strength, announced Daniel Burnham during the building's dedication ceremony in 1903. The project had required innovative scheduling that allowed floors to cure individually while construction continued on upper levels, demonstrating that scientific concrete methods could be adapted to complex urban construction without destroying project economics or extending completion dates beyond acceptable limits. Humphrey's ongoing testing revealed that the Ingalls Building concrete continued gaining strength years after construction, with core samples taken in 1908 showing compressive strength exceeding 6,000 pounds per square inch compared to the 4,500 pounds measured during initial testing. The phenomenon contradicted European assumptions about concrete aging and suggested that American scientific methods produced materials that improved rather than deteriorated over time, fundamentally challenging traditional engineering calculations that assumed maximum strength occurred immediately after curing cycles completed. Chicago's industrial reconstruction provided additional validation when steel companies rebuilding after labor conflicts chose Ransom's methods for factories that required concrete, capable of supporting heavy machinery, while resisting thermal cycling that had cracked European-style foundations within years of installation. The industrial applications demanded concrete that could maintain structural integrity under conditions more severe than typical building construction, testing scientific mixing methods against operational stresses that revealed weaknesses invisible during standard structural analysis. 5,200 pounds per square inch after 5 years, compared to 3,400 pounds per square inch for European concrete in identical structures, Eastwood reported while reviewing comparative testing data from Chicago industrial projects completed between 1906 and 1910. The numbers demonstrated that Ransom's methods produced concrete that not only met initial design specifications, but exceeded them consistently across different applications and environmental conditions, providing mathematical evidence that American scientific construction techniques represented genuine engineering advancement rather than expensive experimentation. Opposition from established engineering firms intensified as Ransom's success threatened their market dominance, with Hermann Schussler organizing formal challenges through professional engineering societies that questioned whether American methods had been tested sufficiently to justify abandoning European techniques with centuries of proven performance. The resistance created political obstacles that sometimes prevented Ransom from bidding on major projects, despite technical evidence that his concrete outperformed traditional alternatives by substantial margins measured through systematic testing rather than observational assessment. The Panama Canal project selection process became a crucial test when the Isthmian Canal Commission evaluated construction methods for the Gatun locks, massive concrete structures that would control water flow through the canal while resisting tropical climate conditions that European engineers had never encountered in their traditional applications. The project required concrete that could maintain structural integrity for generations under conditions that included extreme temperature variations, constant humidity, and seismic activity that exceeded European engineering experience, making it an ideal proving ground for American scientific construction methods. Colonel George Goethals reviewed competing proposals while considering that concrete failure in the Panama locks would compromise American strategic interests for decades, making long-term durability more important than initial construction speed or cost savings that appealed to contractors focused on immediate profits rather than generational performance. The decision represented a watershed moment that would either establish American concrete engineering as superior to European methods or confirm traditional arguments that scientific approaches were impractical experiments unsuited for projects requiring absolute reliability under extreme conditions that tested construction materials beyond normal operational limits. Colonel George Goethals stood beside the massive concrete forms at Gatun Locks in 1913, watching the largest concrete pour in engineering history flow into interlocking sections designed to control the Panama Canal for 2 centuries. 3 million cubic yards of concrete mixed to Ransom's specifications created a structure that dwarfed every previous construction project, but the tropical climate and seismic conditions of Panama tested American concrete chemistry under environmental stresses that no laboratory could replicate. The locks represented the ultimate validation of scientific concrete methods, with failure potentially compromising American strategic interests and success, proving that engineering innovation could surpass European traditions on a scale that would influence construction practices worldwide. The modified Ransom system required cooling pipes embedded throughout each massive concrete block to control the natural heat generated during curing cycles that would otherwise crack structures of unprecedented size. Humphrey had calculated that concrete masses exceeding 10,000 cubic yards would generate internal temperatures approaching 200 degrees Fahrenheit during hydration, thermal conditions that would create expansion stresses capable of fracturing even the strongest concrete if cooling was not systematically controlled. The engineering solution involved circulating chilled water through embedded pipe networks that allowed concrete to cure at optimal temperatures while maintaining the density and strength characteristics that Ransom's methods achieved under normal construction conditions. Every block poured in sections, every section cooled individually, every cure cycle monitored for temperature and strength development over the full 28-day minimum, announced Chief Engineer Arthur Davis while reviewing construction progress that proceeded methodically despite pressure to accelerate completion schedules. The systematic approach required coordination between concrete mixing, steel reinforcement placement, cooling system installation, and form construction that challenged every aspect of traditional construction management, but early strength tests confirmed that the lock's concrete was achieving design specifications that exceeded European standards by margins that impressed even skeptical engineering observers. World War I material shortages created the first serious challenge to Ransom's methods, when steel rationing forced contractors to use inferior cement and accelerated pour schedules that compromised the extended curing times essential for scientific concrete performance. Portland cement prices increased 340% as military construction consumed materials needed for civilian projects, while construction schedules compressed by 60% to meet wartime demands that prioritized immediate completion over long-term durability. Projects attempting to use ransom methods under these constrained conditions experienced 25% strength reductions that gave ammunition to critics who argued that American techniques were impractical during national emergencies. The Quebec Bridge collapse in 1918, though involving steel rather than concrete construction, triggered nationwide panic about American engineering standards that had abandoned proven European methods for experimental techniques that might compromise public safety. Congressional hearings questioned whether American concrete represented genuine engineering advancement or dangerous departure from time-tested European practices that had built infrastructure across the civilized world for centuries. Hermann Schussler testified that war shortages had exposed the impracticality of American methods that required luxury materials and extended schedules unavailable during national crises, arguing that European techniques offered reliability that American experiments could not match under real-world constraints. American concrete methods depend on perfect conditions that rarely exist in actual construction. Schussler declared during Senate committee hearings that examined infrastructure safety following multiple wartime construction failures. European engineering survives because it accounts for material shortages, weather delays, labor problems, and schedule pressures that American scientific methods cannot accommodate. Practical construction requires techniques that work under adverse conditions, not laboratory perfection that fails when reality intervenes. His testimony carried weight with senators concerned about infrastructure reliability during wartime conditions that tested construction methods under stresses impossible to predict or control through scientific planning. Frank Walker from the Bureau of Standards quietly began systematic testing of concrete structures completed before and during the war, collecting core samples and strength measurements that would provide objective evidence about the performance of different construction methods under various conditions. His methodical documentation revealed that structures built with full ransom specifications maintain design strength regardless of construction timing, while concrete mixed with compromised materials or accelerated schedules showed the deterioration that critics attributed to American methods, generally rather than wartime deviations from proper scientific procedures. The post-war analysis vindicated Ransom's principles when Walker's comprehensive testing demonstrated that concrete mixed to scientific specifications performed consistently across different projects and environmental conditions, while structures built with wartime compromises showed stress fractures and strength reductions that European-trained engineers incorrectly attributed to fundamental flaws in American construction techniques. The data revealed that proper implementation of low-water cement ratios and extended curing cycles produced concrete that exceeded European performance standards, but deviations from these specifications for any reason compromised results in ways that traditional European methods could better accommodate through their acceptance of mediocre but consistent performance characteristics. The American Society of Civil Engineers faced mounting pressure to establish national concrete standards that would either validate scientific American methods or restore European techniques as the official foundation for American construction practices. The decision carried implications beyond engineering considerations, representing a choice between innovation and tradition that would influence American infrastructure development for generations. Walker's documentation provided mathematical evidence supporting American methods, but political pressure from established engineering firms and wartime construction failures created institutional resistance to abandoning European techniques that offered familiar mediocrity rather than scientific excellence that required perfect execution to achieve superior results. The 1920 formal adoption of low-water cement ratios as national concrete standards represented triumph for scientific engineering principles over traditional construction practices, but the victory came after years of political struggle that demonstrated how institutional resistance could delay technical progress even when mathematical evidence clearly supported innovation over tradition. Ransom's methods had proven superior through systematic testing and real-world performance, but establishing new engineering standards required overcoming cultural prejudices and economic interests that benefited from maintaining familiar techniques regardless of their technical inferiority compared to American scientific alternatives. The Great Depression transformed American construction priorities overnight, forcing engineers to abandon short-term thinking for infrastructure designed to last generations with minimal maintenance budgets that bankrupt municipalities could not afford. Hoover Dam and the Empire State Building became proving grounds for Ransom's principles scaled beyond anything previously imagined, projects where concrete failure would devastate national morale, while success would validate American engineering permanently against European traditions that had dominated construction since the Industrial Revolution began. The economic crisis created paradoxical opportunities for expensive construction methods that saved money over decades rather than years, making scientific concrete suddenly economical, despite higher initial costs that prosperous times had made politically impossible to justify. 6 Companies, Inc. won the Hoover Dam contract partly because their bid incorporated Ransom's concrete chemistry scaled to handle 3.25 million cubic yards of concrete poured in interlocking blocks designed to cure over 125 years without compromising structural integrity. Frank Crow's construction management adapted scientific concrete methods to mass production techniques that maintained precise water-cement ratios while pouring concrete at rates exceeding 1,000 cubic yards per day. Engineering coordination that required systematic control of mixing, transportation, placement, and cooling systems operating simultaneously across the massive construction site. The project demanded concrete that would function reliably for centuries under conditions that combined extreme temperature variations, seismic activity, and water pressure that exceeded any previous engineering specifications. The cooling system engineering represented the most sophisticated application of Ransom's principles ever attempted, with refrigerated water circulating through over 500 miles of embedded pipe that controlled curing temperatures in concrete masses large enough to generate heat for decades without mechanical intervention. Each concrete block measured 50 feet square by 5 feet thick, dimensions that required individual cooling management to prevent thermal cracking that would compromise the entire dam structure if any single section failed during the extended curing process. Humphrey's calculations indicated that uncontrolled concrete curing in blocks this size would create internal temperatures exceeding 300 degrees Fahrenheit, thermal conditions that would fracture even the strongest concrete through expansion stresses impossible to accommodate through traditional construction techniques. Every block cooled to optimal curing temperature, every section maintaining 46% water-cement ratio despite mass production requirements, every cubic yard tested for consistency before placement, announced Crow, while reviewing daily construction reports that documented systematic application of scientific concrete methods on an industrial scale never previously attempted. The coordination required precise scheduling of concrete mixing plants, transportation systems, placement equipment, cooling water circulation, and form construction that challenged every aspect of traditional construction management. But early strength tests confirmed that dam concrete was achieving compressive strength that exceeded design specifications by substantial margins. The Empire State Building Foundation presented different challenges when architect William Lamb specified concrete capable of supporting the world's tallest building while maintaining the rapid construction schedule that Depression economics demanded for project viability. The foundation required concrete stronger than structural steel to distribute building loads across Manhattan bedrock without settlement or cracking that would compromise the skyscraper's stability, testing Ransom's methods under urban construction conditions that combined time pressure with engineering requirements more demanding than any previous building project in American construction history. John Raskob's financing depended on completing construction within 18 months, schedule pressure that seemed incompatible with extended concrete curing cycles, until innovative construction management allowed foundation concrete to cure, while steel frame construction proceeded simultaneously on upper floors. The systematic coordination required mathematical precision in scheduling concrete pours, steel delivery, and construction crew deployment that transformed traditional building practices into industrial production methods capable of achieving both speed and quality standards that individual priorities had made mutually exclusive in previous construction projects. Testing results from both projects validated Ransom's principles on scales that eliminated any remaining doubt about American concrete superiority over European methods, with Hoover Dam concrete achieving 6,800 pounds per square inch. Compressive strength and Empire State Building foundation concrete exceeding 7,000 pounds per square inch after initial curing cycles completed. The numbers represented mathematical proof that scientific construction techniques could produce materials stronger than required by design specifications while maintaining consistency across different applications and environmental conditions that had challenged traditional concrete methods throughout the history of large-scale construction projects. Core samples collected from 1890s. Ransom concrete structures showed zero structural deterioration after 50 years of service, dramatic contrast with European method concrete from the same era that required extensive repairs or complete replacement due to strength degradation that made older buildings structurally unreliable. The long-term testing provided definitive evidence that American scientific concrete represented genuine engineering advancement rather than expensive experimentation, with structures built using proper water-cement ratios and extended curing cycles maintaining design strength indefinitely, while traditional concrete weakened predictably over decades of environmental exposure. 2020 core samples from Hoover Dam measured 8,500 pounds per square inch compressive strength. Concrete that had actually gained strength over 85 years of service rather than deteriorating like traditional materials that required replacement every 50 to 75 years. The phenomenon confirmed Humphrey's original theories about concrete chemistry, with low water-cement ratios creating materials that continued hydrating slowly over decades, while maintaining density and strength characteristics that improved rather than degraded through extended environmental exposure under conditions that destroyed European-style concrete within normal building lifespans. Meanwhile, interstate highway bridges built during the 1960s using fast concrete methods that prioritized construction speed over long-term durability required billions of dollars in repairs after just 50 years of service, demonstrating that abandoning scientific concrete principles for economic convenience created infrastructure problems that eventually cost more than proper construction would have required initially. The comparison vindicated Depression-era engineering decisions that couldn't afford to build infrastructure twice, proving that American scientific concrete represented practical engineering advancement that modern construction methods had abandoned for short-term economic advantages that created long-term financial disasters requiring constant maintenance budgets that properly built structures would have eliminated permanently.